This is Unit 6, Video 10. In this video, we will talk about Graham's Law. Graham's Law is actually referring to the idea of effusion, and if you remember, effusion is the escaping of particles through a tiny opening, of gas particles through a tiny opening. So if you have a container and it has a tiny little opening here, gas particles can escape, and the rate at which they will escape depends on their kinetic energy and their mass. So we saw these pictures a little earlier, and if you have a balloon filled with nitrogen gas and one filled with helium gas, and you wait some time, say a few hours, a set amount of time, the nitrogen will decrease in size by a little bit, but the helium will decrease in size significantly. And the reason for that is because helium is much lighter. It actually depends on mass. Helium has a mass of about 4. This is just the molar mass from the periodic table. Nitrogen, being diatomic, will actually have a mass of about 28 grams per mole. So nitrogen is quite a bit heavier, helium is quite a bit lighter, and it's because helium is traveling faster, being lighter. Helium is traveling much faster, it will escape faster out of the little hole. It's not because helium is smaller, that is true, but it is really because of the mass difference. Now you'll notice that the sizes of the balloons, so if you roughly say that helium is 4 and nitrogen is 28, that's maybe about 6.5 times bigger, roughly 6.5 times bigger. But the sizes of the balloons are not 6.5 times bigger, the difference in the size. It's actually not a proportionally straight relationship, and we'll see this in a minute. It's actually proportional to the square root of the molecular mass. So it's not, so it is inversely proportional, but it is to the square root and not just to a direct type of relationship. And the neat thing here is, because it is related to the molecular mass or molar mass of the substance, we can actually use Graham's law to solve for molar masses, which is a goal of chemists, to be able to solve for a molar mass, and that's what we will do here. So here is the equation, and what we assume is that both gases are at the same temperature. If the two balloons are at the same temperature, they have the same kinetic energy. So kinetic energy 1 equals kinetic energy 2, and because kinetic energy is 1/2 mv squared, what you can do is you can equal 1/2 mv squared for the first gas to the second gas. You make them equal. And then you rearrange the equation to get rid of the 1/2, so you essentially just multiply by 2 on the other side, and you get yourself this relationship, and then you divide away. And then to get rid of the squared, you simply square root, and you end up with this here relationship. And then if you want to use, instead of v for velocity, because 1/2 mv squared says velocity, if you want to call this rate, this right here would be rate. So think of the rate of effusion, how quickly the gas escapes. You actually have yourself this final equation that's a little cleaner. And this says that the rate of the first gas divided by the rate of the second gas is inversely proportional to the square root of the mass of the second gas to the square root of the mass of the first gas. Notice that the first gas is on top here, and that first gas is on the bottom here, and that shows a reverse or an inverse relationship, since if you were to move this up, it'd be multiplied. And remember, two variables multiplied represent an inverse relationship. So, but it is inverse to the square root of the molar mass, and big M, remember, here is molar mass. So really, this is the equation that you'll be able to use in solving these problems. All you need is, this is Graham's law of effusion, and it essentially comes from the definition of kinetic energy and this idea of effusion, of escaping through a tiny little opening. So all we have to do is a little example problem, and we'll close this concept up. An unknown gas effuses at a rate of only 0.355 times that of oxygen at the same temperature. Calculate the molar mass of the unknown gas. So we measured two gases. The first gas, we'll say gas 1, was oxygen. We'll call gas 1 oxygen. And we'll call gas 2 this unknown gas. And so we know the rate of the gas is 0.355 times that of oxygen. So if we make oxygen's rate of effusion 1, we'll make this gas have a rate of effusion of 0.355. And that's what that needs. So sometimes the way the rates are given may be a bit confusing, but if you write this out, hopefully this will make sense. So usually these rates have units of something per second. So rate is usually some sort of measurement per second. So oftentimes you can say meters per second in our case, moles per second. We haven't talked about molarity yet, but oftentimes it is molarity per second. So just put m per second. Think of this as mass or moles or something. It's actually per second is the unit for it. So what we've got is we've got an equation that says the rate of gas 1 over the rate of gas 2 equals the square root of gas 2. Remember, they're on opposite sides. And then the square root of molar mass of gas 1. R1 is 1, R2 is 0.355, so we can plug those in. So we'll put 1 up here and 0.355 down here. Now, the molar masses of our gases, oxygen has a molar mass of 32. So simply take that from the periodic table. So oxygen has a molar mass of 32.00 grams per mole. And then obviously we don't know the molar mass of gas 2. That is what we're solving for. So molar mass is what we're solving for. Alright, so plug that in. We'll have the square root of 32 will go on the bottom. 32.00. And then the square root of our second gas goes on top. Now what you could do is you can cross multiply and divide, or you can simply multiply the square root of 32 up there and divide by 0.355. So let's do exactly that. Go ahead and grab your calculator, and let's do square root of 32. So we got square root of 32, and then divided by 0.355, and I got 15.93. So hopefully that's what you got. So 15.93 will be equal to the square root of m2. Now to get that square root out of the way, we'll have to square both sides. So with algebra, in this case now, I'm going to get rid of this by squaring this and squaring this. The squaring of this essentially cancels out the square root, if you remember from your math. And really, it's the 15.93 squared that gets us the final answer. So just square that, and you should get a molar mass of 253.8. Now we have 3 sig figs, so really 254, since we begin with 3 sig figs for our data, so 254. And in this case, grams per mole would be the unit because we're solving for the molar mass of the gas. Alright, hopefully this makes sense. What you'll do is simply plug it into this equation, and this is neat because you can use a known gas, in this case oxygen, and just check how quickly an unknown gas effuses, and then determine its molar mass. So 255, pretty heavy gas. Most likely this is just something with a high molar mass. Was what it sounds like. Alright, this wraps up video 10 of Unit 6.